All right, so welcome everybody for the second session for today. And the first speaker in the program will be Jérôme Boillot, who is working with Jerome Feret. And the talk is about symbolic transformation of expressions in modular arithmetic. The floor is yours.
Thank you very much. So let's talk. The work I will present to you is a joint work with Jérôme Feret, and it's about symbolic transformation of expressions in modular arithmetic. So let's start with a bit of motivation. So there is critical code that has to be certified free of runtime errors. And abstract interpretation, as you saw this morning, allows proving properties, semantic properties, and in particular prove the absence of runtime errors. Most of those semantics properties are represent linearity constraints, and in many programming languages, in particular C, there are explicit and implicit modulo computations that are nonlinear constraints. So the proposition is to rewrite expressions to simplify them. And because we get easier expressions, it's easier to identify patterns, and in particular, linear interpolations. So that was the motivating example. So I told you we had implicit modulos in C. Let's see an example. So we take the assumption that integers are stored on 32 bits. It remains general, that's just a parameter of the analysis, but it has to be fixed. So in this example, we have SI that is equal to -1, UI that is equal to 1, and we then compare SI to UI. And because SI is an unsigned integer, there is an integer conversion that is done, and SI will be converted to an unsigned integer. So there will be a wraparound, and SI will be interpreted as 2 to the power of 32 minus 1. So we now want to prove properties, mathematical properties on those programs. So we will represent them in a way such that we can do operations in Z, over Z. Okay? So we will introduce a new tool, a new syntax feature, that is modulo over on an interval. So for every k that is an integer and L and U bounds, k modulo LU is just the remainder of the Euclidean division of k by the size of the interval, so U minus L, and then offset by L. So let's see a few examples. If k is already within the interval bounds, so for example 28, then the modulo computation just acts as the identity. If the size of the outer modulo interval divides the size of the inner modulo interval, then the inner one can be discarded. If the inner modulo is included in the outer modulo interval, then the outer one can be removed. It just acts as the identity. Also, in some cases, two modulo computations can be seen as just a translation of the modulo interval, okay, the modular ring. So here, from 2 to 4, we get 12 to 14. Last example, when we apply the unary minus to modulo computations, then it just is equivalent to applying the unary minus on the sub-expression, the inner expression, and then evaluating it on the modular ring with opposite values. Okay? So let's get back to our example. So here we rewrite the program on left in our intermediate language, where all modulo computations are made explicit. So all the operations are made over Z. So here we can see that we have SI modulo 0 to 2 to the power of 32. So if we do constant propagation, it's just 2 to the power of 32 minus 1. So what we did, what we said just before. So now we want to rewrite, as I said before. So let's consider this example where we have two integers that are x and y, and we have x that is greater or equal than y. And we want to compute the distance between those two variables, so x minus y. In fact, if we evaluated just x minus y without the unsigned int, the cast to unsigned int, it would have been an error, an undefined behavior, because x minus y can overflow, and signed integer overflow is an undefined behavior in C. So this x casted to unsigned int cannot be represented without a modulo, but the difference, x minus y, can be represented, and in fact it's just x minus y, but with the minus of z, okay? So we just rewrote this example in our intermediate language, and then we want to prove that R is indeed just x minus y, without all the modulos. So the idea is that during the inductive rewriting, at each step, we keep the information of the modular ring in which the expression has to be interpreted. So at first, this is the expression we had with all the modulo explicit. First, we apply the unary minus. So as we saw earlier, it's just minus y evaluated in the modular ring with opposite values. And then we can, because here, this modulo ring 0 to 2 to the power 32 divides its size, divides both size of inner modulo computations, modulo intervals. We can just remove the inner ones, and it's just x minus y evaluated in modulo in the modular ring 0 to 2 to the power 32, and x minus y is within the bounds of this interval because x is greater than y. So we can just remove the modulo, and we have finished our proof. We will prove something a little bit bigger by reusing the previous example as a brick. So let's consider this program. We have a variable that is equal to t1 minus x, b that is equal to x minus t0, and r that is just the sum of the two previous values. And what we want to do is to simplify it that those x cancel each other in the addition. So let's do it. We will do an inductive proof, a tree of induction rules, using induction rules. So we have what we want to prove here. And just because all the modular ring we will consider are the same, so within the interval 0 to 2 to the power of 32, and for simplicity, we will just represent modulo evaluation by underlaying them, okay? And here the color has no meaning. So let's start. We will reuse what we showed in the previous slide. That is, if you have a subtraction of two expressions and both of them are interpreted in the same modular ring as the outer one, then we can just remove the two inner ones. So let's begin. We have A. By doing symbolic constant propagation, we can rewrite it as T1 minus X, evaluated in the right modular rings. Then we can just apply the diff mod rule, okay, by removing the two inner modulo computations. We can do exactly the same with B. And then we can just rewrite in this expression the values of A and B, okay? So it does this, and we reuse again the same rule, diff mod. So we can remove the two inner modulo computations. So it's just T1 minus T0 evaluated in the ring 0 to 2 to the power 32. And then because, again, like in the previous slide, because T1 minus T0 is within 0 to 2 to the power 32, because T1 is greater than T0, we can just remove the modulo computations and we are done. So that's the kind of rules we will use to rewrite our expressions and remove the modulo by keeping intermediate modulo evaluation during the inductive process. But we want this process to be sound, so we don't want to rewrite expression and to rewrite something that would be false, that wouldn't match the initial expression. So we will first define the semantics, of course. So we get a program state that is raw, that is just a function from variables to elements of Z. So the values, possible values of E1 plus E2 are the possible value, are X plus Y, where X is a possible value for E1 and Y is a possible value for E2. And then the semantics correction is that for a given set of properties P, if the properties P hold, then the values of E prime, when interpreted in the modular ring M, over-approximate the values of E. So this is really this inequality here, that is, we do another approximation of the values of E. And then we want to prove that our rewriting, so E can be rewritten as E prime modulo M, satisfies is sound, okay? That's exactly this equation. The problem is what happens, we would like to rewrite E times 1 divided by 0 as just 0. But is it possible? Is it possible? Of course not, because we would miss the division by 0 error. So what we do is first to enhance our syntax, our semantics. So we had this expression for the semantic, and we just will add a second term that will be the potential errors. So here, the potential errors of E1 plus E2 is just the potential errors of E1 and the potential errors of E2. Then we can see what it means for harder expression, for example, the division. Then we just have the possible values of the division, and the errors are the errors of E1, the errors of E2, and if the denominator can take the value 0, then a new error that represents a division by 0. Okay, then we have to update the semantics correction. That is, if the properties P hold, then the values of E prime, when interpreted in the modular ring M, over-approximate the values of E, when the potential errors omega 1 have already been reported. And that is the equivalent inclusion test. So let's conclude about the inductive rewriting. We automatically and correctly simplify arithmetic expressions into sum, product, and quotient of linear forms before they are passed to the underlying abstract domain that will get easier expressions. And there are many more automatic rules in the paper, more than 30, and the rewritings are proved correct. And those simplified expressions is the recognition of patterns, and that will be the topic of the next section, that is pattern recognition and simplification. And we will come back to our motivating example, that is linear interpolation. So what is the linear interpolation of f? So here we have f, that is the function. In x0, it takes the value y0, in x1, the value y1. Then we have x that is between x0 and x1, and we do just the linear interpolation of it. So here in x, it will be this value. So I just represent this process into this function, this little code except, where you have exactly the same expression, y0 plus, etc. Here, we remark that x minus x0 divided by x1 minus x0 is something between 0 and 1. So, when we multiply it by y1 minus y0, it's something between 0 and y1 minus y0. And yeah, that's what we would like to rewrite it in. So any value between 0 and y1 minus y0. And this would be enough to prove this assertion. And this corresponds to non-determinism. So in our intermediate language, there exist only intervals currently to represent non-determinism that are intervals. So for example, 0 to 28 is just any value between 0 and 28. The problem is that it's difficult to represent relational properties with them. So we will introduce a new operator to model non-determinism, that is the convex join. So E1 convex join E2 is just any value between E1 and E2, and the errors are just the errors of E1 and the errors of E2. And it models non-determinism, but it has expression as bounds. Why bounds like this? Because there is no order between those bounds. So 0 convex join 28 is the same as 28 convex join 0. So let's see a few examples. 0 convex join 28 is just any value between 0 and 28, so the interval 0, 28. X, convex join x is just value of x. We don't lose the information of x. And the convex join does not depend, that's what I said just before, does not depend on the order between its operands. So if x less or equal than y is proved later, it follows that x is less or equal than x convex join y, and that is less or equal than y. So now we can use this new definition, new operator in our intermediate language to express properties about the example we had just before. So this part in red can be rewritten as something between 0 and y1 minus y0. Then by adding it with y0, we can just rewrite it as y0 convex join y1, that is any value between y0 and y1, and then we are done with this proof, because here y0 is less or equal than y1, so the order is fixed. So that's nice, and we can even handle more complicated patterns, like bilinear interpolations, where we are interpolating a function f that has that takes two variables as arguments. First one x and second one y, and we're in x I yj, it takes the value zij. Sorry. So we can see that this corresponds to a pattern of linear interpolation. So that's something between 0 and z00, c00. So this is a bigger interpolation that is nested, and that's again something between 0 and z00. And then we add three similar patterns. So the sum is just something between 0 and the sum of the zij. So now we know that it's something between 0 and the sum of zij, and we want to prove that it's between 0 and this. Okay, so how can we prove that? We are using octagon's domain to represent constraints that are plus or minus x, plus or minus y, less or equal than the constant. The problem is that octagons cannot represent properties, constraints about more than two variables, and there are four variables in this inequality. So we have a problem. This solution is to use symbolic constant propagation. So we just rewrite our inequality into, we propagate the value of r symbolically, and we get just 0 convex join the sum of the zij minus the sum of the zij, that is less or equal than 0. Then we can just simplify it to get minus the sum of the zij convex join 0, that is less or equal than 0. And then the interval domain is enough to conclude because we know that all these zij are positive. In fact, in both Astray and our artifact, there are more refinements, and in particular, for linear interpolation patterns, if we have a strict comparison, then we get a better approximation. So we know that R is less strictly than Y1. And there are also other patterns that are handled. So in conclusion, what we propose is a cheap automatic wrapper that simplifies arithmetic expressions before they are passed to underlying abstract domains, in particular in the presence of wraparounds that couldn't be represented without it, while keeping the expressiveness of underlying abstract domains. And these simplified expressions are better to search patterns, such as linear interpolations, because you know it's product sum or a quotient of linear expressions. All those rewritings are formalized by a deterministic inference system that always terminates. And we introduced the convex join operator in the intermediate language to take advantage of relational properties while manipulating non-determinism. And this domain has been implemented in Astray, at least the ENS version, but also in an available toy abstract interpreter powered by Apron that you can see, you can find on Zenodo. Thank you.
Thank you, Jerome. Are there any questions? Yes, question in the back. One moment, I'll pass you the mic.
So, thank you, that was very interesting. I have a question. When do you decide to introduce your operator? Because both forms have different characteristics, so you can you are going to lose information when you rewrite it in your expressions. So what's the criterion?
Okay, that's a good question. In fact, we had already in mind at the beginning that we wanted to prove properties about linear interpolations. That was really a motivating example. And we already know what we wanted to assert at the end, what properties we wanted to prove. And to prove this property, we had to represent non-determinism, but with relational properties. Okay? So at first, it wasn't like this. It was a bit different. It was another operator that was something that was taking one argument, that was an expression, and that was representing something between 0 and this expression. And then we iterated a bit and found out that it was better to represent the convex join. And that it could be maybe interesting also on other applications, on other, to represent other properties.
Yes, one more question, one moment.
Yes, thanks for the nice talk. I was wondering if the rewrites always improve precision, or if there are some cases where the rewrites lower precision of the overall analysis, and how do you deal with that? And
yeah, thank you. Okay, so because we are rewriting, I mean, it depends on the other abstract domains, because for example, for the linear interpolation, it rewrites it into here y0 convex join y1. But if by another way we could find properties about x0, x1, and about x, where it is in between, maybe we could get better approximation. So that's not always the best representing the best properties, but I think for to get those invariants, it's really convenient.
Thanks.
Any further questions? All right, then let's thank you.
I think it's just another.
Oh, sorry.
Hi, I mean, I would be interested to know, I mean, and you can be quite rude about this, it's fine. So we had a paper in SAS, and it was about taming the wrapping of integer arithmetic. And we had a wrapper there which operated on general polyhedra. Okay. Is it that you found that wrapper failed to work for linear interpolation, or was it sort of too weak for that?
You mean polyhedra?
Sorry?
Is the polyhedra domain?
No. It's we had a wrapper that did a form of relaxation, which actually took a polyhedra and relaxed it with the
taming.
Yes,
I see
right.
Okay.
Yeah. Okay. So is that method too weak for applying linear interpolation?
I think so. Let me think a bit. But I think, you wouldn't represent. So what would you have with this? You would have a division of. No. You wouldn't have something precise enough because you want here to recognize that x minus x0 divided by x1 minus x0 is within 0 and 1. And this couldn't be, I don't think this would be expressed by the polyhedra even with the wrapper.
Okay, that's good. Thank you.
All right, any further question? This time really not, so let's thank the Jerome.